In the second part of the chemistry trend presentation, I will resume the discussion of the high discharge rate applications. So batteries that were designed for notebooks were failing in these applications because of too high resistance was causing too high IR drop, and that resulted in much smaller usable capacity. But several new chemistries have been developed or optimized to use for high power applications in such a way that they have a very small internal resistance and small resulting IR drop. One example is NMC chemistry, nickel cobalt manganese cathode, that is popular with automotive applications because it has a high power capability just like a manganese spinel, but much higher energy density. It can support up to 10 C discharge rate, and it has a nice sloping voltage profile that doesn't cause problems with trying to determine state of charge or state of health of these batteries. Another chemistry that was optimized for high power operation is lithium iron phosphate chemistry that was popularized by A123 Systems company. Even though the company itself is now bankrupt, several other companies are manufacturing these cells. If you look at the profile here, at discharge rate of from 1 ampere to 40 ampere, you can see very similar usable capacity if they are discharged to around 2 volt. It is important for high power applications to keep your system voltage correctly adapted to the battery performance. You don't want your system voltage to be here, for example, very close to flat portion of the curve. So if system voltage would be, say, 2.5 volt, you would get only 20% of your capacity. But if you set it at 2 volt, you get most of your capacity out of the battery. This is especially critical for high power applications because there the IR drop is causing voltage profile to go down. You can see lithium iron phosphate also has excellent cycle life. You can see here that in this case it goes 1000 cycles before it loses 20% of capacity, but in other cases it can go even up to 5000 cycles. One problem with lithium iron phosphate is it has about twice lower energy density compared to traditional lithium ion. So one way to address this problem is to raise its voltage. So original lithium iron phosphate has a low voltage around 3 volt, but by replacing iron with some other metal, for example cobalt, you can raise the voltage up to 5 volt and still get close to the same milliampere hour value, and this way the overall energy of the battery can increase by 30%, and that would bring it almost close to the lithium cobalt oxide based cells, but still maintaining the high safety and high power capability because of the phosphate structure of the cathode, which is very stable. The other player in the high power applications is lithium titanate anode batteries. In this case we are talking about anode and not a cathode. Cathode can be the same, lithium cobalt oxide or any other choice, but the anode in this case is a very stable compound that doesn't react with a solvent, so it doesn't have to build a passivating layer as opposite to graphite. And the main reason why lithium ion battery degrade is that the passivating layer is not completely stable and still leaks some of the solvent, which reacts with lithium and grows the passivating layer. That results in higher impedance and loss of some of the lithium from the system. But in titanate, since it doesn't react with the solvent, there is no passivating layer and it is not growing, so that mechanism of degradation does not exist. For that reason you can achieve up to 20,000 cycles with this cell, and it also has a very high rate capability because there is no passivating layer resistance, and there is also very good low temperature impedance performance because the diffusion rate in lithium titanate is very high, and also because there's no passivating layer, you can prepare this material in nanoform, and so since you have very small particles, the diffusion rate doesn't matter that much. So if we talk about the future chemistries, something that will be beyond 5 years, 5 to 10 years time frame, we can be use our imagination and not restrict ourselves to some chemistries that are already there. We could just look at the periodic table of elements and try to find some element that will have the highest energy density when put together in the battery. So we need for a battery two elements. One that will give us electrons, basically metal, another element that will take electrons eagerly, which is typically a non-metal. So the metals are on the left side of the periodic table, and the stronger is the metal, the more left it's going to be. The same thing is non-metal are the more right on the periodic table they are, the stronger they accept electrons. So if we pick something from the far left, and we also want both elements to be on the top of periodic table because we want them to be light to achieve the higher energy density by weight. And the weight is increasing as you go down on the periodic table. So what satisfies this condition the best for the metal is lithium, because it is on the top left. And on the top right we find fluorine. Unfortunately, fluorine is a gas, and it is also extremely aggressive, so it's very hard to store it in anything. Nobody was able to make a battery out of it for that reason. But not very far from it is oxygen. It's also quite close to the right on the periodic table, and it is on the top, so it's pretty light. It is still a gas, so it has a low density, and it would be difficult to make battery out of it. It would have a very bad energy density, but luckily it is present in our atmosphere, so we could take it directly from the atmosphere and we don't have to store it. That makes lithium oxygen battery extremely promising, and it has a very high energy density to 5.5 thousand watt-hour per kilogram. If you compare it to existing lithium cobalt oxide based lithium ion battery right now, it is close to 400 watt-hour per kilogram, so it is about 20 times higher energy density. So certainly with that kind of battery, the cars would be able to go even more than they go with the gasoline storage right now. Unfortunately, this chemistry has a lot of various problems, and I will discuss about it as I go in more detail for each particular one. Another interesting choice is lithium sulfur. It also has a very high energy density, and sulfur is right below oxygen in periodic table, so it is almost as aggressive, but it is a little bit heavier. But even so, it gets a energy density of about 2,500 watt-hour per kilogram. Another interesting candidate is zinc oxide battery. The zinc itself is heavier than lithium, but it exchanges 2 electrons instead of 1, and so that doubles the energy density, and that provides it a pretty decent energy density of about 1000 watt-hour per kilogram if combined with oxygen. So let's look a little bit closer at these three promising chemistries. So lithium sulfur is probably the one that is the closest. It has been under development for a long time already. In particular, the Sion Power Company have been working for over 20 years on this chemistry. One big problem with silicon is that it is an insulator, so it is very hard to convert all of it basically during the battery operation. So you have to combine sulfur with some conductive material that will deliver electron very close to the sulfur, basically within a couple of nanometers to sulfur. That means that you need to mix sulfur with a huge amount of carbon black or some other conductive material, and that reduces the energy density of the battery. So practical cells are right now at about 350 watt-hour per kilogram. Another problem is that sulfur is kind of soluble in a solvent, especially in presence of lithium sulfide. It forms a polysulfides, where there's many chains of sulfur are basically connected to one lithium, and those polysulfides are soluble, and they act as a shuttle that delivers sulfur from sulfur cathode to anode instead of reacting as a battery should do. And that wastes sulfur and causes the problem with the cyclability, and it will have also very high self-discharge rate. So there are different attempts to solve this problem. On one side, by using solid electrolytes, that is pretty promising. On the other side, by trying to encapsulate sulfur into something which will prevent these polysulfates from building. As encapsulation have been promoted by the group of Professor Cui. In particular, he suggested a very interesting approach. So many groups before tried to deposit some films on top of cathode or anode particles to protect them. The problem with that is that when the battery is charged and discharged, particle is expanding and contracting, and so the layer deposited on it cracks and basically becomes useless. But the idea of Professor Cui is to put it inside a shell that is bigger than the particle, what he called yolk shell encapsulation. So in this case, it will be like in this figure on left upper side. When a material is discharged, the particle is smaller than the shell, and during charging, particle is expanding, but it still remains smaller than the shell at the end, so the shell does not crack. And this way, they demonstrated amazing cycle number with the sulfur-based battery. They demonstrated 1,000 cycles with the still high capacity of 1,500 milliampere hour per gram. That is 5 times bigger than capacity you can get with the traditional cathode material. The same kind of benefits have been demonstrated for anode material that expand a lot. For example, silicon is a promising material. It has a huge energy density for lithium intercalation, but it expands more than 100%. That caused basically very bad cyclability for silicon containing batteries. But if it could be encapsulated like this, or maybe encapsulated in some kind of a solid matrix, you could achieve good cyclability and high energy density. Another promising battery is zinc air. It is already used as a primary battery. In fact, it holds a record for the highest energy density primary battery, and for that reason, it is used in the hearing aids batteries. Hearing aids is one place where all the high energy chemistries are competing, because it's not important, the cost is not a problem there. The problem is the battery has to last as long as possible between replacing. And so the higher energy density always appears there first. So zinc air primary is already working, but it's very difficult to make it rechargeable because the zinc oxide is also an insulator. And once it is formed during the discharge, it's very hard to convert it back. First of all, efficiency of converting it back is very low, so you need to have some kind of catalyst to reduce the impedance of this conversion. And there have been interesting developments of using some nanomaterials on which this zinc oxide is deposited, so that you have a electric conduction very close to the zinc oxide. And then there are also some catalysts that make zinc oxide grow in an amorphous way, so it is easy to access and not as a solid crystal. Another promising development is to use zinc oxide not in a solid form, but in the form of a suspension, kind of like a toothpaste. So instead of trying to bring electrons to a zinc oxide particle that is immobilized somewhere on the electrode, we make it so that we keep mixing this paste, and so that every particle of zinc oxide eventually will come close to the electrode and have a chance to get discharged. So this is kind of a zinc oxide, zinc oxygen flow battery that is pretty promising for the grid storage applications. Grid storage is a big area of development right now, because the problem is that power grid right now is not capable to support a huge swings in power production. But as we add more and more renewable energy to it, such as solar or wind power, it is very unstable and can be turned on and off at any moment when the little cloud comes between the solar panel and the sun. So batteries are being installed in the grid so that you can absorb energy when it is produced and then release it when it is needed. The problem with the grid storage is that you need a huge amount of energy for very cheap price for watt hour. And all traditional battery chemistry don't come even close to the cost that is needed in this kind of huge energy storage applications. What is used right now for grid storage is what is called pump hydro, which is basically a lake where water is pumped up the dam when the energy is available, and then there is a turbine that is used to create energy when energy is needed. So as you can imagine, this is extremely cheap per watt hour. Basically, if you need more energy, you just make a bigger lake. But the same thing doesn't work for batteries. You need more energy, you need to add electrodes, you need to add active materials and so on. So the zinc oxide might actually be one system that could compete. Finally, the holy grail is the lithium air, because it has the highest theoretical energy density for any system. It has a lot of problems to be solved. First of all, the rate capability of them is not very good, because for any air battery you need to absorb oxygen from the air, and since any gas is present in low density, you kind of need to concentrate it first before it will react. And the way to concentrate it is to use pretty expensive catalysts, usually platinum, iridium, that kind of absorb some amount of oxygen on the surface. So the reaction rate is pretty slow. That means you cannot deliver much power from these systems. It is still acceptable for applications like hearing aids, where not much power is needed, but it has to operate for a long time. So I expect lithium air will first appear also in hearing aids, but it will be not rechargeable. If you want to make it rechargeable, additional problems come in, and that is it builds again, once it is discharged, it builds lithium peroxide, which is also highly insulating material. So you have to create an electrode that has a very high surface area and brings the electrons directly to the surface of this material very close, so it can tunnel. So a lot of nano engineering is needed to make this battery to have decent rate capability and to make them rechargeable. You also need to develop some fancy catalysts that will control the form in which the lithium peroxide is formed, so that it doesn't form crystals but forms some kind of a porous amorphous material that can be accessed. So there is lots of various problems that are left to be solved, and so I don't expect lithium air to be on the market for next 5 to 10 years. First, it will appear probably within the next 5 years as a primary battery. Another interesting futuristic chemistry in general includes under category of flow batteries. Flow batteries are not completely new. They have been around for over 30 years, but they are still not widely known. The main problem with the battery is that if you need more energy, you need to add more electrodes, more active materials, and once they're used up, basically there's no way to bring any more. But with flow battery, the idea is to put the active material into solution, so both anode and cathode are actually liquids. And so if you used up your anode and cathode, you can add more. And if you need more energy density, you just increase the size of your tank, and tanks are cheap. So this is a perfect kind of a battery design for grid storage applications, because that is exactly the case where you need a lot of energy, but not necessarily a lot of power. And power and energy are kind of separated from each other, because if you need more power, you need more electrodes. You make bigger electrode stack. If you need more energy, you make bigger tanks and more solutions with your active materials. One of the popular flow batteries is a vanadium redox flow battery, because both anode and cathode material are using vanadium salts. So if some of them are leaking through the membrane, it just loses some energy, but it doesn't make the battery defect after that. There are several new developments going on with the flow batteries. One is a lithium-ion suspension flow. The idea is to take basically materials from a lithium-ion battery and make a suspension out of them again, just like a toothpaste or ketchup, and then pump them to make a flow battery out of it. This way you can have high voltage and high energy density. Because one of the big problem of the flow batteries of any kind is that since they have a solvent which is useless in terms of energy, it brings the energy density is low. Another approach is to try to use organic materials for the flow battery. So both anode and cathode would basically be organic liquids. So that way you also can have a high energy density. But that would also make it more expensive, probably, because organic liquids are usually more expensive than inorganic salts. Well, to summarize all of the trends that we have discussed today, so the energy density growth of lithium-ion battery continues according to the trend over the last 20 years, or about 160 milliampere hour per year. But in percentage that has decreased from the beginning. We can expect that the growth will continue now with the silicon and silicon oxide batteries, and 18650 cell is now available at 3.5 ampere hour. We can expect that because of the cost structure, lithium cobalt oxide is gonna get replaced more and more with nickel and manganese in NCA and NMC chemistries. These chemistries already provide a similar energy density. They are especially adapted in not multi-cell applications where there's more than one serial cell used, because minimal voltage of the cell phone devices of 3.4 volt does not allow to take advantage of these new chemistries. The same thing is true for the newly developed silicon anodes. They also add most of the energy below 3.4 volt. The other direction of development is to go to higher voltages to increase energy, and there the most promising are overlithiated metal oxides, which is OLO. It can be expected within the next 2 to 5 years to be on the market. And lithium iron phosphate has a good longevity and power capability, but to make it also high energy density, the high voltage olivine materials like the lithium cobalt metal phosphates are very promising. Both of these require development of high voltage capable electrolytes. High rate options are available, that is NMC, lithium titanate, or lithium iron phosphate. And for the grid storage, there's a lot of various chemistries, both traditional and new, are competing. Lithium iron phosphate inherently is not expensive because the iron is very cheap, but because it requires a nano manufacturing, right now the cost is pretty high. So if that could be reduced, it could be competing. Lithium titanate itself is expensive, but it provides such a long cycle life that overall system usage cost could be pretty low. And of course we have to see what will happen with zinc air flow batteries. Lead acid itself is being used too because it's very cheap. Lead is very well recyclable, and everybody know how to deal with this chemistry. So the near-term most promising technologies are silicon anode, that's already on the market and will keep increasing the content, overlithiated oxides, high voltage olivines, 5 volt electrolytes, and yolk shell encapsulation for any kind of material. And the long-term lithium sulfur is already appearing on the market. Then we can expect to see rechargeable zinc air and eventually lithium air. Well, thank you very much for staying with us for this presentation, and I'm hoping to bring you a next update of the battery trends in about 1 year. Thank you very much.